Hello everyone, this is our feedback system project video, and the purpose of this project is controlling the angle of the arm that is coupled with the shaft of the motor. And to succeed this, we use a motor drive which is fed from the Arduino board, and we use the Arduino as a controller. And the operation of the project is demonstrated by my friends.
We can change the arm angle using a graphical user interface, and we can set desired angle from here. Now it's set to 0 degrees, and I will change it to 60 degrees. As you can see, arm is changed immediately. And now I will set it to minus 45 degrees. And as you can see, it's immediately changing its angle. Now my friend will show you what happens if you change arm angle manually.
Now I want to show you what will happen if I change the arm angle handling, and our desired angle is 0 now, and I change it to 45 degrees by hand and it's come back to 0. Let's change it to 45 degrees, and it's now on 45 degree. I really changed angle. As you see, it never changes. Now I want to show you step 3. I pick some k values from the root locus graph, and firstly I will consider the underdamped case. Kp is the 4 and desired angle is 60, and you see the response of the system. And now I will write minus 60, and you observe the response again. If I increase the Kp values from 4 to 8, now I firstly come to 0, and you see the oscillations. And by the way, if we increase the Kp values, we increase the overshoot magnitude. I change to 60 degrees, and it comes 60, and you see oscillations increases and the maximum peak is increased. And settling time is not changed because of the psi omega n is not changed in this case. If we observe the underdamped, overdamped case, experimentally we couldn't observe it because the Kp values are about 0.1719, and in this case our system does not work because of the friction of the motor, and I set it 0.19, but there is no motion and there is no noise. There is a problem in our system because of the motor non-idealities. If I give a disturbance by hand when the Kp is 4, and you cannot enter, and it comes back. If we increase the Kp values, it will respond fastly, and more oscillation will occur.
For the step 4, we need to design a proportional controller to succeed a 10% overshoot. And to do so, we benefit from the MATLAB plot and the function root locus. We derive the transfer function from with the parameters that we determined in previous steps, and we choose 10% overshoots, and the Kp value come out that's very little to rotate the motor. So we choose another Kp value that corresponds to 25% overshoot, and let me show this. We set the desired angle to the 50 degree and Kp value for 4, and you see the motor come to 50 degree with an overshoot approximately 25%. And the corresponding rise time and fall time approximately come out that it's The peak time is 0.23 seconds and the settling time is approximately 0.45 seconds. For step 5, we need to make some observation related with the KD value. So we set the KP and KI values to 0 and we set KD 1 to observe for the small values of KD. And when I rotate the arm, my hands, you see that motor command is the PWM signal is changing with the changing angle. And let me increase the KD value to 5. And when I rotate the arm with my hands, you see that the PWM signal is again created. And for more large KD values, we see that motor commands almost always on. So the possible reason for this is when we increase the KD, we increase the response time, we decrease the response time. So for very large KD values, system acts very fastly and the PWM signal is generated, always generated, so it's almost always on position.
In the sixth part of the project, we are asked to design a PD controller such that it has the 10% overshoot and has the half settling time of the step 4. As my friend indicated, our design wasn't able to achieve the 10% overshoot due to insufficiency of motor, so we designed the system with 25% overshoot, and we did this step 6 according to 25% overshoot. First of all, we set a value for alpha, and then we rearranged the characteristic equation so that alpha is in the characteristic equation is in the form of 1 plus alpha times T of S, where T of S is the open loop transfer function, and we plotted the root locus for this transfer function. And as I said before, we had given a value for alpha. To achieve the half percentage settling time, we doubled the psi omega m value so that we, from the root locus plot, we observed the k value which corresponds to double psi omega m value. And at the end we have one value for alpha and one value for k, which leaves us kp value as k times alpha and kd value as k. And when we enter these values to graphical user interface, now I'm changing the angle from 0 to 60. As you can see, there is a non-zero error, and system is comparably fast, we can say, and motor arm angle is set to 60 degrees. In the seventh part of the project, we are asked to design a PID controller which has the same values of KP and KD as in part 6. And we set the sum max value to a non-zero value to prevent motor from saturating. Setting sum max value to a non-zero value, I made KP and KD values same as in part 6 and made KI value 20. Now we will observe what happens if we change arm angle to 60 degrees. And as you can see, error is 0 degrees. This is because we use PID controller. KI controllers provides the 0 error case. However, it brings some slow operation, and this is the trade-off between accuracy and speed. And that's all about PID controller and step 7. In the step 8 of this project, we are asked to design a PID tuning controller using Ziegler-Nichols design table. This Ziegler method is based on the zero placement to the transfer function. It's basically starts with obtaining the Kp values at which the system is critically stable, and the oscillation frequency and Kp values determines the PID controller parameters. These parameters are obtained using the Ziegler table, as you can see here. And using this Kp value and oscillation frequency, different parameters are obtained for PID and PID controller. This Ziegler method basically places zeros such that root locus plot is crossed from points in which we want the system to cross. For example, for Kp values at which the system is critically stable, using Ziegler method and designing some PID controller, we can obtain a stable system such as underdamped. And this is the basic idea behind Ziegler-Nichols controller.